Hello grade 12s, I hope you are still good. It's me once again with another past paper. I know you guys are in the middle of your June exam, and most of us, and actually almost all of us, have written paper 1, paper 2 for maths, and we still have science waiting for us. And for today's video, I want us to go through a physics paper 1 past paper. As you can see, this is from 2021, so it is a national senior certificate paper for May-June examination. So yeah, let's get to it. So as usual, first thing first, we have the multiple choice part, and I want us to go through the multiple choice questions and also see how you can get like the full marks, because remember, multiple choice is 20 marks. It is possible to get all the 20 marks, but it's also possible to not grab all the marks. But yes, we are here for all the marks. Okay, so question 1.1, a constant net force acts on an object moving in a straight line. Which one of the following quantities associated with the object will remain constant during the motion? So they've told us that there is a net force. So we know that if there is a net force and it's constant, we relate that with Newton's second law, because yes, in order for us to have a net force on an object, it means the object has a mass and it is accelerating. So one quantity that will have to be constant, yes, mass is one of them, and acceleration also. But because we don't have the mass, it means the constant quantity will have to be acceleration. So acceleration must be constant for the force to be constant. Question 1.2, the weight of an object on the surface of F is W. What will be the weight of the object on the surface of another planet of the same mass as that of the Earth, but twice the radius of the Earth? So if we are dealing with the weight and we are dealing with Earth, we know the formula. Weight is equals to G big M, big M over D squared. So if we are saying the weight of the first object was W, so the weight on the surface of the Earth is W, and then what is the weight of the object on the surface of another planet? So it means if we are bringing another planet and they say the mass is the same, it means we still have big M, but what is changing now is the radius is twice that of Earth, so it's gonna be 2D squared. Remember, if you are doubling the radius, you have to put that inside of the bracket so that they can both get the exponent 2, which would give us G big M over 4D squared. And in this case, it means we have 1 over 4 G big M over D squared, which was equals to small w. So the answer would be 1 over 4 small w, which would have to be option A. So with this kind of questions, what you need to do, you write the original formula or the original equation, and then you go and put the changes that they do to the equation or to that formula, and then you take out the numerical values. You still want to extract the original formula, so that you now can see the factor that the first weight has changed by when they doubled the distance or the radius. Okay, I hope you are still with me. Quickly going to 1.3, the diagram below shows a cricket player moving his hands downward from position 1 to 2 to 3 while catching your ball. If you think about this, this is very common. If someone throws something to you, you don't push your hands toward the object that is coming towards you, but what you do is you move as backward as you can, and so that the object, when it hits your hand, it doesn't cause any pain. So the question is, which one of the following statements correctly explains why the cricket player moves his hands downward. So before we even look at the options, let us explain the reason, or let us explain the application behind this. So when we were doing impulse, we had said with impulse, when you want a force that an object has to experience to be small, you need to extend the time. So before we look at the options, let us think about why does the person has to lift or has to move their hands downward. So what they do is they want the ball to hit the hands, the cricket ball to hit their hands without causing much pain, or with the force being smaller. And this takes us now to impulse. We know with impulse that we had said from the equation of impulse, delta t is inversely proportional to F net, meaning if you are increasing the time that it takes for an object or for this ball to hit the person's hand, if you are increasing the time, you're going to lessen the force. The force is going to be smaller, and this is one of the reasons why the person is moving their hands downward, so that the time that it takes for the ball to hit their hands is smaller. No, it's bigger. So it being bigger, it means the force is going to be smaller, and the force being smaller, it also means change in momentum. It's also going to be smaller because F net is directly proportional to change in momentum. This now, if we look at the options, the impulse on the ball is decreased. Nope, that is not the case. The change in momentum of the ball is increased. No, that is being decreased. The change in the momentum of the ball is decreased. Yes, that is correct, but also the time it takes to change the momentum of the ball is increased. That would be the correct option. We want to extend the time that it takes for the ball to change its momentum, and that means the ball is going to have less force when it lands on the person's hands. I hope it makes sense. Question 1.4. Consider the motion of a small stone thrown vertically upward until it reaches its maximum height. Ignore the effects of friction. Which of the following? So here they are telling us that the ball is in free fall. The moment they say ignore friction, which one of the following combinations of graphs correctly shows you the momentum and the gravitational potential energy of the stone change with time? So we know that with momentum, the formula for momentum is mv, and gravitational potential is mgh. So this would mean that as the ball is going up to reach the maximum height, what we know about maximum height is that the velocity is 0. So it means the velocity of the ball as the ball goes up decreases. As a result, we expect momentum to decrease. So it means for momentum, we want a linear decreasing graph. We have, I'm just going to zoom in. So we have two of them. We have B and D. So it means with that, we are eliminating C and A. And then now let us decide on the gravitational potential energy. As the ball is moving up, what happens is, yes, as the time continues, the height is going to increase. And if height increases, we know the mass and the gravity is constant. That is not changing since the ball is in free fall. So it means what is changing is the height. So as the height increases when the ball goes up and approaches maximum height, we expect the potential, the gravitational potential energy to increase. But for this one, because on the graphs we don't have, if it was a graph of gravitational potential energy and the height, yes, we would have a linear increasing graph. But because we have gravitational potential energy and the time, we are now going to expect like a parabolic or a quadratic increasing graph, which now eliminates that one, and the only option that we have is D. So this is because, yes, time does not directly affect gravitational potential energy. As time goes, what changes is the height, and then the change in the height is the one that affects U. So this is why the graph is not a linear, because it's not a direct relationship, but there is a factor in between the height, the gravitational potential energy and the time. I hope you're still with me, grade 12s. Let us move now to question 1.5. A boy and a girl having different masses are initially at rest at point P. They slide down, so they say they have different masses, which I'm going to highlight. They slide down different parts of a water slide as shown in the diagram below. Ignore the effects of friction. So we are also saying they are not experiencing any friction, so it means the only force that they experience there is weight. Consider the statements below regarding the boy and the girl. So only conservative forces act on both the boy and the girl while they are sliding downward. Because we want to tell you which ones are correct. This one applies because we are ignoring friction, so it means they're only experiencing weight, and we know that weight is a conservative force. The boy and the girl each have the same gravitational potential energy at P. So at P, remember, gravitational potential energy is mgh. Yes, the height is the same, g is the same, but their masses are different, so they cannot experience the same gravitational potential energy. On reaching point Q, the speed of the girl is equal to that of the boy. Is that correct or not correct? That would not be applicable also, because still they have different masses, so there's no way that they can have the same speed. So it means our correct option here is going to be A only. Okay, I hope you're still with me. Question 1.6. An astronomer observes that the light spectrum of a star has been blue shifted. Keyword: how have the observed frequency of light from the star and the distance between the star and Earth changes? So let us go back to revise the spectrum. We know that according to Roy G. Biff, we know that Roy G. Biff, I hope I wrote it correct. We know that on the red shift we have a greater wavelength and a smaller frequency. Then as you move towards the blue side, you have a smaller wavelength and a greater frequency. So it means, because they say it has been blue shifted, that would mean that it is going to experience a higher frequency and a smaller wavelength, meaning that would be option B. I hope you are still with me. Question 1.7. A small negative point charge Q is situated halfway between two identical spheres P and Q. So I'm also highlighting identical. Carrying identical charges as shown below. So we have charge P and Q, and then in between them we have a negative point charge. So the first question, the question: sphere P exerts an electrostatic force of magnitude F on sphere Q. What is the magnitude of the net electrostatic force experienced by the point charge? So the point charge is halfway, and what we should know is that since these two charges, these two identical spheres are identical, it means this one is going to exert a force of the same amount on Q. This one is also going to exert a force of the same amount on Q. The forces are just going to be in opposite direction. For example, if we say this exerts a force of X newtons and this exerts a force of negative X newtons, to find the net electrostatic force, we would just say x plus negative x, and that's gonna be 0. So that would lead us to choosing option A. Okay, 1.8, I'm going to skip it because we don't have it under June examination. It's not part of the scope. In the electric circuit diagram below, all resistors are identical. Okay, I need to erase that because I was working on that. In the circuit diagram below, all resistors are identical. Ignore internal resistance of the cell and the resistance of the connecting wires. When switch S is closed, the reading on voltmeter V1 is 3 volts. What will be the reading on voltmeter V2? So when we close that switch. So now let us look at how the voltage is going to flow through the resistors. So we know according to conventional current, the direction would be that, and it will get to this point here where we have a parallel branch, and we know in a parallel branch voltage is the same, so they get the same voltage as the one that comes from the battery. So it would mean that if 3 volt, because they said the reading on V1 is 3 volts, if 3 volt went in that direction, in this direction, it means 3 volts also, I'm just going to use a blue pen, also went into that direction. But now when it got to this connection, you can see that we have now more than one resistor, and this one resistor is in parallel to these two is in series to these two that are in parallel. So it would mean that that 3 volt will now have to be shared between the R and the 2 R's there. So if we consider those 2 parallel R's there, I can try to find R total. We know that for 1 over R total, we have 1 over R plus 1 over R, and that's going to be 2 over R equals to 1 over R total, and our R total is okay, let me just quickly write that. R total would be R over 2. So it means if we say this parallel connection there is represented by R over 2, it means the voltage is going to be shared between the resistor that has a magnitude, half of its magnitude, and that one. And we know the relationship between resistance and voltage: the greater the resistance, the greater the voltage. So they are directly proportional, meaning they're going to share the 3 volts in the ratio of 1 over 2 is to 1, meaning if that gets, so it means the resistance, the voltmeter reading on this one should be double there. It means if it's 3 volts, that's going to be 2, and that's going to be 1. Hence the reading on that was going to be 2 volts, the reading on V2, because it should be double of what is on 1 over 2. Okay, so question 2, we have Newton's law as per usual. We have an 8 kg block on a rough horizontal surface is connected to a 2 kg block by a light inextensible string passing over a frictionless pulley as shown below. The 8 kg block moves at a constant speed when pulled by a 29.6 newtons force to the right. The frictional force on the 8 kg block is 10 newtons. So I'm going to highlight some important information. For example, yes, they've already bolded that constant speed. So what we know about constant speed, before we can even go to the questions, we'll say when we have constant speed, it means we have 0 acceleration. We don't have any acceleration, and having no acceleration, it means F net will also be 0, because F net is ma, but a is 0, so m times a is 0. Question 2.1, state Newton's second law of motion in words. I'm not going to write this one, I'm just going to say it by mouth. So Newton's second law of motion states that when a net or when a resultant force acts on an object, it causes the object to accelerate in the direction of the force, with the acceleration being directly proportional to the force and inversely proportional to the mass of the object. So that is Newton's second law in full. You have to make sure that you mentioned the whole law so that you can get the full marks. 2.2, draw a labeled free body diagram for the 8 kg block. So the 8 kg block, remember they had said it's on a rough horizontal surface. We have frictional force, we have F applied, and then because we also have a string, every time when you have a string, it means you are going to have tension. So remember, with a labeled free body diagram, we use a dot to represent the object, and we always have the weight, which is Fg. We always have the normal force, and we have F applied, which I'm just gonna give the letter F. Then we have friction. Remember, friction is in the opposite direction, so frictional force is to the left since the object is moving in that direction. And also because of the string, remember guys, tension is always away from the object, so our tension is gonna be to the left also. And also you must be careful when you draw the free body diagram. If it's 5 marks, it means we need 5 forces, so the number of marks always correspond with the number of forces that you must include on your free body diagram. Question 2.3, calculate the tension in the string. So we want to find the tension, and because the system is, the tension that we have there is the same tension there. If we are to draw the free body diagram for the 2 kg block, the only forces that are acting there would be Fg and tension, which is always away from the block. And since we have a constant speed, since we have a constant speed, it would mean that F net is 0. And if we now make use of the 2 kg block, the F net on the 2 kg is going to be F net equals to 0. And because the system is going up in that direction, it means you are taking up as positive, and any other forces that are downward would be negative. So the only forces that we have are T and Fg. So I'm going to say positive T minus Fg is 0, because Fg is downward and T is upward, making T to be equals to Fg, which is mg. We know Fg is mass times gravitational acceleration, and then the mass is 2 times 9.8. 2 times 9.8, that's going to give us 19.6 newtons. So the tension in the string is 19.6 newtons. So now the 29.6 newtons horizontal force is now increased to 50 newtons. So now we no longer have 29.6, we have 50 newtons. Apply Newton's second law to each block and calculate the magnitude of the acceleration of the 8 kg block and the tension in the string. So it means if we change F, we're going to have a new tension. And because they also want acceleration, it means we are no longer moving at a constant speed. When the force changes to 50 newtons, it means acceleration is no longer constant. So because they also had said we must use Newton's second law in each block, I'm going to start with the 2 kg. So for the 2 kg, Newton's second law is F net equals to the mass for the 2 kg times acceleration. And because it is now on the same string, it means it's the same acceleration for both the 8 kg and the 2 kg. So our F net, we had seen we have T, we also have Fg equals to ma. We don't have T, but mg is 9.8 times the mass. Okay, that should be the mass times 9.8. So that would be 2 times 9.8 equals to 2 times acceleration. T is T minus 19.6 equals to 2a. So if I make T the subject of the formula, is 2a plus 19.6. And then now going to the 8 kg, let us look at the forces that are acting according to the free body diagram. We have tension and frictional force in the opposite direction, meaning we're going to give them negatives, but the applied force would be positive. So it means we have F net equals to MA, and under F net we have applied force minus tension minus frictional force equals to MA, meaning I just want to make T the subject of the formula. So it means applied force minus frictional force minus MA equals to T. Frictional force is 10 newtons. Okay, applied force, not frictional force. Applied force is 50, and our F applied is 50 newtons. Of frictional force is negative 10, is 10, and then the mass is 8 times 8 times A, because we have an unknown acceleration is T. So 50 minus 10, that's 40, minus 8A equals to T. So we are solving simultaneously, meaning we're going to have 2A plus 19.6 equals to 40 minus 8A. So 10A, so I'm just taking the 8A to the other side, equals to 40 minus 19.6. And 10A would be 40 minus 19.6. That is 20.4. Therefore, acceleration would be 20.4 divided by 10. That's 2.04 meters per second squared. So that would be the acceleration. And then they also had said they want the tension. So for the tension, you still refer to one of the simultaneous equation. So it means tension would be 2 times the acceleration that we got, which was 2.04 plus 19.6, and that gives me 2 times 2.04 plus 19.6. That gives me a tension of 23.68 newtons. So this is with the question, it's 7 marks. So you do simultaneous every time, not every time, but most of the time when you have a string that attaches 2 objects, it means those objects, they share the same acceleration, and because they are on the same string, they also have the same tension, meaning on your simultaneous, the 2 unknowns are your acceleration and your tension. Okay, so this is it with Newton's second law. Now we can quickly go to question 3. So question 3, we have a ball of mass 0.06 kg is thrown vertically upward from a balcony of 3 meters above the ground. The ball reaches a maximum height h above the ground as shown in the diagram below. Ignore the effects of air resistance. And question 3.1, name the force acting on the ball while it is in free fall. So we all know that whenever something is in free fall, the only force that is experiences is the force of gravity. So the answer for that would be the force of gravity. Force of gravity, or the weight. And then now they give us the velocity time graph below represents the motion of the ball from the instant it is thrown upward until it hits the ground. So we have the velocity versus time graph, and write down the acceleration of the ball at time 1.02 seconds. So they want the acceleration of the ball there. So what do we know about the velocity versus time graph is that when the line crosses that x-axis line or the time line, it is where you have a velocity of 0, and we know velocity is 0 at the maximum height. So it would mean at the maximum height they want acceleration, so it means the ball, since it is in free fall, acceleration is always going to be 9.8 meters per second downward. Don't forget direction, guys. downward. Since it's 2 marks, if you just say 9.8 meters per second, you're only getting a single mark. Question 3.3, consider the areas A1 and A2 shown in the graph above. Write down the numerical value represented by the differences in areas of A1 and A2. So we know that an area in a velocity versus time graph represents a displacement. So the area under A1, if we now look at the velocity versus time graph in this, because we would say when we describe or when we interpret this graph, we would say the ball was projected up with this velocity, it went all the way up, and then here it was at the maximum height, meaning there at 1,02 it was here, and then it now started coming down, which is now represented by area 2 until it hits the ground. And as you can see, the area 2 is quite longer. So it means when you subtract the two areas, you are getting a displacement. And remember, a displacement is the shortest cut from initial to final, meaning the displacement is just that 3 meters over there, because displacement, unlike distance, is the shortcut between the initial and the final. So if the person starts there, if the ball started there and ended there, the shortest cut is that one. So subtracting the areas would give us the displacement, meaning it's gonna be 3 meters. Just a single mark, meaning you don't have to do calculations, you use the graph. 3.4, calculate the speed at which the ball is thrown upward. So let us look at what we have, because we want V initial here. We are looking for V initial. We have V final because it reaches maximum height. Okay, I'm just going to come and write that here. It reaches maximum height, so it means the V final there is going to be 0. And we also have the time, because time 1,02 tells us the time that it took for the ball to reach that part. So the time from there to there, because it's from V initial to maximum height, it's 1,02. So the formula that we can use VF equals to VI plus A times time, because we have everything there except for V initial. VF is 0. We are looking for the V initial. Our acceleration is always negative 9.8. And please bear in mind, in this question I'm using positive as upward as positive and downward as negative. That would mean acceleration, because it's always, gravitational acceleration is always downward, I'm gonna give it a negative. And then the time was 1,02. And then taking the V to the other side, negative V would be equals to negative 9.8 times 1,02, and that gives me 9.8 times 1,02, it gives me 9,996 negative, meaning V initial, if we round it, it's gonna be 10 meters per second. They wanted the speed, so we don't have to give direction, so it means the V initial there, we got it to be 10 meters per second. I hope you're still with me, guys. So it means out of the velocity versus time graph, what we have gotten so far is that the area under the graph represents the displacement. Then we need to find the height h. So we are looking for the height there. So it means the height from the ground to the maximum. Already we have a portion of this height. This one, it was the 3 meters. So we need to find the height from 3 meters going up. We can still use the ball to say what was the height of the ball from when it was projected up until it reaches maximum height. We can use delta y is trying to think of the easiest formula. We can still use vi times t plus 1 over 2 at squared, and our v initial we have found it to be 10. So I'm keeping it as positive 10 because it's going up. The time was 1,02 plus 1 over 2. Acceleration is always 9.8, and then time is 1,02. Okay, that is very squeezed. Just gonna sort that out. So it's negative 9.8 and 1,02. 1.02 squared. Please don't forget this exponent 2. So I'm just going to quickly plug that on my calculator. 1/2 times -9,8 times 1,02 squared. So that gives me delta y is 5,10. So the delta y that I've calculated is the distance from there to there. It gave me 5,10, but because we are looking for the distance from the ground, I'm going to add the 3 plus 3, and that's going to be 8,10 meters. So it means h is 8,10 meters. I hope you're still with me. And then question 3.5. After hitting the ground, the ball bounces vertically upward and reaches a new maximum height in 1,1 second. Calculate the work done by the ground on the ball while the ball is in contact with the ground. Okay, so we need to find the work. It's 6 marks. So what they've given us is they've given us the time that it took for the ball to reach the maximum height after bouncing vertically upward. So we know for work done, we have different formulas of work done, but since under this chapter, under VPM, we are dealing with velocities. The formula that we can have in mind initially or first would be V net equals to change in EK, because EK has velocities. And then our change in EK, it would mean that we have we need to find V final, because what we have calculated, we have found the velocity of, okay, we don't have any of that, so that is 1/2 m Vf squared minus Vi squared. So this Vf and Vi, this would be, remember the ball hits the ground. I'm just gonna make an illustration. This is the ground. The ball comes in and hits the ground, and then it leaves the ground. It hits the ground with the V initial, the velocity that it hits the ground with, and then it leaves the ground with a V final. So this would be the velocity that it leaves the ground with. So I'm just trying to check if we did calculate the velocity that it hits the ground with. It doesn't look like we did. So we have to find two velocities. We need to find the velocity that the ball hits the ground with and the velocity that the ball leaves the ground. So for the first part, for me to find this first velocity, I'm going to use, because what I'm looking at here is it's coming from the top here. So I'm going to use the 0 as V initial, and then I'm looking for V final. I have delta H, so I can use an equation that has V initial, V final, and delta H, meaning I can use Vf squared, it's Vi squared plus 2a delta y. I'm looking for Vf, but my Vi is 0 plus 2 negative 9,8. Delta y is the 8,10, this one, because it's the height. If you go up there, that's the height from there to there. So I'm gonna use I'm gonna put it as negative also, because why? We are taking downward as negative, so negative 8,10. And I'm just gonna write the final answer. I'm gonna plug that and then also do the square root of it. So square root of 2 negative 9,8 negative 8,10. That gives me 12,6 meters per second. Remember, it's plus or minus because I've square rooted. Okay, let me include this crucial step. So Vf is plus or minus square root of just a moment, square root of 158,76. The answer is going to be negative 12,6, because if it's plus or minus, it means I'm choosing. Muzi, It means I'm choosing, so it's going to be negative 12.6 meters per second. So that is the V final. So it means the velocity there, yes, it's V initial, but I'm going to use it, I calculated it as V final. So that would be 12.6. So now I need to find this velocity. This is for the pathway it goes for the second maximum height. So this is when the time is 1.1. So they've given us the time. They've also given us, what do we have? We also have V final, because if it reaches maximum height, it means V final is 0. So I'm looking for V initial. V initial, Vi plus AT. No, V final is V initial plus AT. V final is 0. I'm looking for V initial plus negative 9.8. The time is 1.1. So V initial would be negative 9.8 times 1.1. That gives me 10.78. So this is that velocity, 10.78. So now that I've gotten both the velocities of the velocity of when the ball hits the ground, which is that one, the velocity of when the ball leaves the ground, it means I can now use V net is change in EK, because I have now the velocities 1/2, then the mass of the ball was 0.06. So that would be 0.06, and then V final, because it's positive, is going to be 10.78 squared minus, okay, I'm just going to use a blue pen because I'm writing black on black now, 10.78 squared, excuse me guys, I don't have space, minus, and then V final, because no, V initial would be that, because it was negative, I'm going to put it as negative 12, but it won't matter because I'm going to square it anyway. And now the total work done by the ground would be 1/2 times 0.06 times, so V final is 0.78 squared minus 12.6 squared. So that gives me the work that is negative 1.28 joules. So that is the final answer. So this is it with question 3 on momentum, no, on VPM. It means whenever they want you to calculate work under VPM, you need to take note that the work is, you can use work is change in EK because you have velocities at most. Okay, so now we are jumping onto question 4. Okay, now starting with question 4. Question 4 is on momentum. So we have a simple rocket system consists of 2 parts, A of mass 3 meters, not 3 meters, A of mass 3m and B of mass 2m, as shown in the diagrams below, and B is stacked on top of A. So as you can see, we have the 2 diagrams before the explosion. B was stacked on top of A, and then after explosion we can see them separating. And the first question, state the principle of conservation of momentum in words, for 2 marks. I'm not going to write it down, I'm going to say it by mouth. So the principle of conservation of momentum states that in an isolated system, the total linear momentum is conserved, or it remains constant. So that is the answer that is worth 2 marks, because they're going to mark keywords. In an isolated system, that is where the first mark comes from. Then the total linear momentum remains constant. That is where the second mark comes from. So they say the rocket is traveling vertically upward, as we can see on this diagram, at a constant speed of v when an internal explosion causes A to move downwards at a speed of 1.3 volts. 1.3 V, not volts, V. So yeah, after the explosion, we can see A moving downward at that velocity and B continuing to move up. Ignore all external forces on the rocket and calculate the velocity of B in terms of V immediately after the internal explosion. So we want the velocity, meaning we want V final for B after the explosion. And so please note, guys, if you state, for example, under these questions, if they ask you to state a principle, 99% of the time, the next question after that, state the principle of conservation, you have to use the principle of conservation of momentum formula. So if they say, for example, also in the other chapters, state the work energy theorem, then the next question they ask you to calculate, you have to use 99% of the time, you use work energy theorem. So for this one, we are going to use conservation of momentum. And with conservation of momentum, if we write it, I'm just trying to get some space. If we write the conservation of momentum for this for the system, we're going to have the mass of A and V initial of A plus the mass of B and V initial of B equals to the mass of A and V final of A plus the mass of B and V final of B. Remember, this is the law of conservation of the principle of conservation of momentum. So because A and B, this is for before explosion, these two were stacked together, so it means their masses can be added. So I'm going to say the mass of A was 3m, and remember, guys, the m is not a unit, it's just your 3m is the mass, so you put it together with the m, it's 3m, and the mass of B is gonna be 2m. And then they were moving with velocity V, which is that one. Then after explosion, A is the one that moved downward, so I'm gonna have 3m because the system was initially moving up. I'm taking upward as positive, and then anything that moves downward, I'm gonna give it a negative, meaning for A, I'm going to give it a negative 1/3 V, because they said the velocity was 1/3 V plus 2m times VF. So we are looking for VF. I'm sorry, I don't have, okay, I do have space actually. Yeah, so we are looking for VF. So 2m plus 3m, that is going to be 5m times the velocity equals to, so 3m times negative 1/3 m, so the 3 and the 3 will cancel out. I'm going to have negative mv plus 2m V final, which is what we are looking for. We are looking for the V final of B. The 5mv and the negative mv are like terms. I'm just gonna move the mv to the left. It becomes a positive, equals to 2mvf, and that would be 6mv equals to 2mvf. So because I'm looking for vf, it means V final for B is going to be 6mv divided by just 2m, and the m and the m cancel. 6 divided by 2 is 3v. So that would be the velocity, because they said velocity, it means we also have to state the direction. Since B is going up after the explosion, we are going to say 3v meters per second upward. That is the full answer. Remember, direction is very important. If they say calculate the velocity, you need to state the magnitude and the direction. If they say calculate, let's say speed, yes, you just have to state the magnitude. If they say calculate the magnitude of the velocity, they are being specific. You're only giving us the magnitude, you don't have to put direction. So that would be the velocity of B after explosion. And then question 4.3, it's based on the graphs. The graph below shows the average force exerted by A on B during the internal explosion as a function of time. So we know, guys, always if you get a graph of force and time, it always represents impulse all the time, because we say impulse is what? It's F net times the time. So you must know every time when you are looking at a graph of force and time, you are looking at an impulse graph, which is going to help us answer 4.3. Name the physical quantity represented by the area under the graph. So if you look at, let's say, because we have a rectangle, it means the area is going to be base times height. The base is time and the height is F. So that takes you to F net times time. So the physical quantity would be impulse. Remember, whenever they talk about physical quantities, these are the things that you can calculate under physics. You can have impulse, you can have momentum, you can have force, you can have work. Those are physical quantities. But this one, because the area under the graph, you are saying force times time, then you are representing impulse. And then they ask us to redraw the graph in your answer book on the same set of axes. Sketch the graph of the average force that B exerts on A as a function of time for 2 marks. So it means you have to redraw the very same graph, and then we need to show the force. So before we can draw the graph, let us think about, or let us find out how is that force going to be, because the graph was showing us the average force exerted by A on B during the internal explosion. So it means when the system exploded, A exerted a certain force on B, resulting in B going up and A itself going down. Why did A go down? That is because B also exerted a force on A during the explosion. So they want us to show now the graph for the downward arrow. And according to, guys, remember Newton's third law, we say when object A exerts a force on object B is going to exert the force of the same magnitude on A but opposite direction. So it means we are going to redraw this graph. On the graph we have the time in seconds, we have average velocity, average force in newtons. Okay, that doesn't look so nice, but I tried. And the original graph that we had was this one, to say yes, the average force is somewhere there. But if we are now looking at the force that B exerts on A, it's going to be the same force but opposite magnitude. I mean, it's going to be the same force, meaning same magnitude but opposite direction, meaning it's going to be the same graph. It's just going to be like a mirror of this one across the x-axis. So to say now the force is the same magnitude but opposite direction, then that is what they want from us. So this is it with question 4. And the next thing that we have is question 5. And next, question 5. For question 5, we have a demolition ball is used by a crane to break the wall of a building, as seen on the diagram. So the demolition ball has the mass of 1,250 kg, is lifted by the crane to a point R. So point R is there at the height of 5.8 meters above its lowest position in 60 seconds. Ignore air friction. So we do have the diagram where we can see the crane, and we can see that it has lifted this demolition ball. The mass of this ball is 1,250 kg, and it is at this point R, which is 5.8 meters away from its lowest resting point. The first question is define power in words for 2 marks, and I'm not gonna write it, I'm gonna say it by mouth. Power is the rate at which work is done. That is the definition of power. And then question 5.2, calculate the average power dissipated by the crane in lifting the demolition ball to point R. So we want the power that the crane uses to be able to keep this ball at this position. So if you check, we have time. They've given us the time at which this demolition ball was being held at point R, meaning the formula of power that has time would be power equals to work divided by time. And then now, yes, the time we have seen it is 60 seconds, but for work now, what work? So we want to calculate the work that the crane uses to keep the ball at that position. And because the ball standing at position R, the only thing that it experiences is the force of gravity, it would mean that yes, the work that the crane has to, or the power that the crane has to use to keep the ball there will depend on the weight of the ball. So it means for our work, we are going to say mg delta x cos of theta is equals to T. So our mg, that would be 1250 times 9.8 times okay, I need enough space. So I'm gonna drag it there. So we have 1250 times 9.8 times 5.8, and then our cos is gonna be cos of 0. Theta is gonna be 0 because yes, the work is, the force would be in the same direction, or maybe it's because also the ball is standing stationary. So that would be times 1, all divided by 60 seconds. So I'm gonna quickly plug that on my calculator. 1250 times 9.8 times 5.8 divided by 60 seconds, and that gives me the power that is 1184.17 watts. So that is the power that the crane dissipated in order to lift the demolition ball. And then now they say the demolition ball is released from point R, and it strikes the wall at the lowest point of its swing. So it will strike the wall at this point. Then after striking the wall, the ball then moves 0.25 meters horizontally into the wall before coming to rest. So we can just indicate that to say when it got to the wall, it moved maybe for about that distance, 0.25, and then now it was at rest, meaning V final is 0. The first question, define the term conservative force. So a conservative force for 2 marks, it is a force whose work done on the object is independent or of the path taken. So a conservative force is a force that does the work on an object, and that work is not depending on the path taken. And then is the force which the wall exerts on the ball a conservative or a non-conservative? So the moment the ball hits the wall and it starts to move further inside of the wall, so that force is going to change because it will depend on how far did the ball move within the wall. So it's gonna be a non-conservative. So it's non-conservative. State the energy conversion that takes place during the downward swing of the demolition ball. So at this point, because here the ball was stationary, the only thing that we had was gravitational potential energy, because we had a height, we had the mass, and then as it started moving, we started now to have a velocity. So it means we are moving from potential energy, gravitational potential energy to kinetic energy. So potential, okay, let me write that using those letters, but you need to write it in words. So you're moving from potential energy to kinetic energy. So potential energy, we can also use EP. This is because initially the ball was not moving, it was stationary, we didn't have any velocity, but as it was released from point R, it now acquired a velocity, so there was kinetic. Using energy principles, calculate the magnitude of the average force exerted on the ball while it moves into the wall. So we want the force as the ball was moving from this point, this red path there, from this point to that point, when it was moving for that 0.25 seconds, no, 0.25 meters, what was the force that the wall was exerting on the ball? So already we have stated that within the wall we have non-conservative. So it means, if for example here we said non-conservative, so it means there we are going to use work done by non-conservative force equals to the change in kinetic energy plus the change in potential energy. So yeah, it means the force there, the average force that we want, we will get it from the F at delta x, cos of theta equals to 1 over 2m v final minus v initial, and they must have exponents 2 plus mg h final minus h initial. So if you check there, we do have delta x, we have the mass, we have v final because they said it will rest after 0.25 meters. We don't have v initial, we have m, we have g, we have h final, we have h initial, because also if you think about it moving horizontally, it would mean that we don't have this part, because the height is just, yeah, we don't have potential energy there, since we had said also that we are converting from potential to kinetic. So it means this part is going to be 0. So it means what I'm going to do, I'm going to find v initial. And if you think about v initial, the ball came the moment it was released from R, where the v initial was 0 at R. So this was at R, then it moved for about 5.8 meters and it landed just at the wall. So we want the velocity in which it now hit the wall with. I'm just gonna work that on this small space there. So what do we have here? We have delta y, we have v initial, it's 0. We are looking for v final, so we can use vf squared equals to, because it was on the air, it also means it was free falling, so we are going to use the negative 9.8. So vi squared plus 2a delta y. We are looking for v final. Our v initial is 0, and we have 2 negative 9.8 times, because it's going down, I'm going to put negative, okay, I'm going to use a different pen because I'm writing with black to black. Negative 9.8, negative 5.8. I'm making them negative because I'm taking downward as negative, and it's coming down. That would give me 2 times negative 9.8 times negative 5.8. That gives me 113. So vf squared is 113.68. So the v final is gonna be square root of that, and that gives me 10.66. So this is the velocity that the ball hit the wall with, meaning it's the velocity that we will use as v initial between the 0.2 meters. So I'm going to now plug in my values because I have everything. So we are looking for f, x is 0.25, cos is going to be cos of 180, because we want the force that the wall exerts on the ball, so that force should be in the opposite direction. Equals to 1 over 2, 1250. V final is 0. Is it 0? Yeah, it is 0 because it rested. And then that's 10.66 squared plus this part. I'm gonna write it as 0 because we don't have any potential energy since the ball is moving horizontally. There's no change in the height, so it means the height, when we do the change in height, will be 0. So the whole thing is gonna be 0. So I have negative 0.25 times the force, negative 0.25 times the force equals to, then the left hand side gives me negative 71022.25. So f is negative 71022.25 divided by negative 0.25, and that gives me 2,804.089 newtons. So that is the force, and that is, yes, worth 5 marks. I hope you're still with me, guys. I hope you're still following. I hope it's all making sense. And I'm going to jump into question 6 on our Doppler effect. So question 6, we have a learner in a car moving at a constant speed of 10 meters per second along a straight horizontal road. And then okay, let me read again. A learner in a car moving at a constant speed of 10 meters along a straight horizontal road records the frequency of sound emitted by a distant stationary source. So here we have a source that is playing some sound there, and then that looks like Wi-Fi. How is sound? Okay, some sound. I hope, yeah, this looks like sound. And then the learner is the one that is moving. The learner is in a car, and that car is now moving. And yeah, so the car is the one that is moving. So the learner then repeats the recording on the frequency of the sound when the car travels at a new constant speed of 20. So this was done twice. The first time the car was moving at 10 meters per second, and it was the learner recorded the frequency, and then the next the car was moving at 20 meters per second, then the learner recorded the frequency. The graph below, not drawn to scale, is obtained from the results. The recorded frequency, we have the speed of the car and the recorded frequency. So the first question, it says state the Doppler effect. So I'm not gonna write it, I'm gonna say it by mouth. So Doppler effect, it states that the change in frequency or pitch of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So that is the definition of Doppler effect. 6.2, use the graph to answer the following questions. Write down the frequency of the sound emitted by the stationary source and give a reason for your answer. So if we look at the graph, we have three different frequencies. The first frequency is here when our speed was 0. The second frequency is there when the speed was 10, and then the third frequency was there when the speed was 20. So it means the frequency of the sound emitted by the stationary source is when there was no movement. So this is like what is the actual frequency of the sound source? That is going to be 700 hertz. And then the reason for that, it's because the velocity of the car was 0. Velocity of car is 0 meters per second. So I hope it makes sense, guys. Think about it. If I'm just standing next to a speaker that is playing sound, and I'm not moving, the speaker is sitting next to me, what the speaker is playing is what I'm actually hearing. But once I start to move away from the speaker, or just to change the distance between me and the speaker, what the speaker plays is not exactly what I hear. So this is why I'm saying it's gonna be the 700 hertz, because this is when the car was stationary. And then the next question, in which direction is the car moving relative to the source? Choose towards or away. So now we want to tell what it was, the car moving towards the source or away from the source. Also think about it. If I am standing, let's say, how do I put it? If I'm standing there and there's a sound source there that is playing some great music, I can't draw a speaker, but yeah. And then if I move closer, I'm gonna hear more than what the speaker plays. But if I move away, I'm gonna hear less than what the speaker plays. But if you check there, we had 700 hertz. That is what the speaker, the sound source was playing. But now as the car was moving at that 10 meters per second, the learner, or who's that? Yeah, the learner recorded a frequency that is smaller. So the frequency of the source is greater than the frequency of the listener. This would mean that the learner and the car were moving away, because what they were actually hearing was less than what was playing. That is because the distance was increasing, or the wavelength. So I'm going to say away, and the reason for that, I will say the frequency of the source is greater than the frequency of the listener. And then question 6.2.3, calculate the speed of sound in air. So they didn't give us the speed of sound in air, so we can calculate it. You can either use the 10 meters per second, 20 meters per second as your VL. I'm gonna choose to use the 10 meters per second. Equation, we know it states that FL equals to V plus or minus, okay, it equals to V plus or minus VL divided by V plus or minus Vs times Fs. So what we are looking for here, we are looking for just the V, which is the frequency of speed in air, speed of sound in air, which is the velocity of sound, or the speed of sound in air. So we need to remember, guys, with this equation, that's where you have to decide if you're using plus or minus. So firstly, because we have seen our source is not moving, the listener is the one that's moving, so I'm gonna say VFL equals to, because the listener is moving, V plus or minus VL over just V, because the velocity of the source is 0 since the source is not moving. Then now we have to sort that one out. We had stated on 6.2.2 that because we had said the listener is moving away, we expect the frequency of the source to be greater than the frequency of the listener. So we want this to be smaller. And remember, if you want that to be smaller, it means what? It means denominator must be bigger and numerator must be smaller. Yeah, numerator must be smaller and denominator must be bigger. So in order for our numerator to be smaller, we are going to put a minus there, and then we have V times Fs. Now we can start plugging in our values. Okay, so now dividing the everything by 0,299, it means that V would be equals to, so 10 divided by 0,0299, it gives me 334,45 meters per second, and that is our final answer for the V, which is the speed of sound in air. And now getting into question 7, the second last question. So we have two charged spheres, R and S, are both stationary on a smooth insulated surface, inclined at an angle of 25 degrees to the horizontal. Sphere S of mass 0,01 kg and carrying the charge of -6 times 10 to the power -9 coulombs is connected to 0,03 meters long light inextensible string attached to a point P at the top of the incline. They further say sphere R carrying a charge of 5 times 10 to the power -9 is held such that the distance between the spheres between the centers of the spheres is R, as shown in the diagram below. We are ignoring the effects of friction. So sphere R exerts an electrostatic force of magnitude 1.2 times 10 to the power -3 newtons on sphere S. Question 7.1 states Coulomb's law in words. Yes, I'm going to say it by mouth. So Coulomb's law says that the net or the electrostatic force between or experienced by any two objects, it is directly proportional to the product of the magnitude of the charges and inversely proportional to the squared distance between the charges. 7.2, calculate the distance R between the spheres. So we have electrostatic force, and we have the magnitude of the charges, and we have stated Coulomb's law, meaning we're going to use the formula for Coulomb's law, QR QS over R squared. Okay, and now plugging in our values. Our K, we know it's 9 times 10 to the power of 9, and then the charge, remember when you put the charges, you don't have to put the negatives there. The charges just go in there as being positive. 6 times 10 to the power -9 and 5 times 10 to the power -9, all divided by R squared, and our R, we don't have it, it's just going to be R squared. And also remember we have F. Okay, it's fine, I can plug in the 9 times 10 to the power of 9 times 6 times 10 to the power -9 and times 5 times 10 to the power -9, and that gives me 2,7 times 10 to the power of -7. It's divided by R would be equals to 1,2 times 10 to the power -3. Then I multiply the r with that. I'm just going to drag it to that side. So I have 1 comma 2 times 10 to the power negative 3 times r squared. So the r has to be with an exponent 2 equals to 2 comma 7 times 10 to the power negative 7. R squared equals to 2 comma 7 times 10 to the power negative 7 divided by 1 comma 2 times 10 to the power negative 3, and that gives me 2,25 times 10 to the power negative 4, and then the square root of that. So if I square root 2,25 times 10 to the power negative 4, that gives me 0,015 meters. So we have gotten r to be 0,015. So r there is 0,015 meters. Draw a labeled free body diagram for sphere S. So you want a free body diagram for that, since it has mass of 0,01. So it's 4 marks, meaning we need 4 forces. The first forces would be our Fg, and we also have a normal force, and then we have tension in that direction, and then we have the other force of I'll just call it Fr on S. So it is the electrostatic force between the two charges. That would be the free body diagram. And then question 7.4, calculate the tension in the string. So we want to find the tension in the string, and we also need so to find the tension in the string, let us consider S, because it's the one that is attached to the tension, and they had said that they are stationary. So if they are stationary, it means we don't have velocity. If we don't have velocity, it means we don't have acceleration. If we don't have acceleration, it means F net is also 0. So I'm going to use the fact that F net is 0 because they are stationary, and the forces that I'm going to use, we must also remember anything that is inclined, it's gonna have Fg parallel, because we need the component of Fg. So considering my direction, I'm going to take downward as negative, and okay, let's see, that is negative and that is positive. Yeah, I'm going to take downward as negative and upward as positive, meaning I'm going to have a positive tension minus FRS minus Fg parallel equals 0. Because I'm looking for the tension, it would mean that tension now equals FRS plus Fg parallel, and then FRS we got it to be 1. So FRS is the electrostatic force, 1 times 2, 1.2 times 10 to the power negative 3. Fg parallel is 0,01 times 9,8 times sin of 25, and that's mg sin of theta. So 1,2 times 10 to the power negative 3, 0,01. Can I just confirm if the mass is 0,01? Yes, it is 0,01. And we also have 9,8 and sin of 25, and that gives me just a moment, let's see. So I have 1,2 times 10 to the power negative 3. I have mg, which is 0,01 times 9,8, or it should be, they should be added, sorry. So there must be a plus there. I'm just going to quickly fix it, because now I see I've multiplied everything. Plus, okay, I need a bigger pen, plus 0,01 times that, which I'm also going to fix. Then I have T to be 0,04 newtons. So that is our T. And then, okay, now finding the net electric field at point P. I'm just going to remove that, and we have the charges, we have the distance. Remember that was 0,015 meters. So I'm going to start with R of not R but the electric field on P due to S. So that's going to be K QS over R squared, and that's 9 times 10 to the power of 9. the charge for Q, not for Q but for S, would be 6 times 10 to the power negative 9, and then R is going to be just 0.03 squared, and that gives me 9 times 10 to the power 9, 6 times 10 to the power negative 9 divided by 0.03 squared, and that gives me 60,000 newtons per coulomb. And then the electric field that P experiences due to R is going to be KQR over R squared, and then our K is still 9 times 10 to the power of 9. Our QR is 5 times 10 to the power negative 9, and then the distance is 0.3 plus 0.03 plus 0.015, that gives me 0.045 squared. So the answer would be 9 times 10 to the power of 9, 5 times 10 to the power of negative 9, negative 9 divided by 0.045 squared, and that gives me 22,222.22 newtons per coulomb. We also need to consider direction. So between R, because remember, if P is it's just a point, we use positive point charge to say P is going to be positive. So between S and P we expect attraction, and it would mean that we expect then it means we expect the electric field to be pointed towards S. So this is I'm gonna give it because it's down the slope, so it means when I put it there I'm gonna write it as negative. And then for your EPR, because between R and P they are both positive, we expect repulsion, so the electric fields on P would go away from P. Therefore we're going to say that is upward, and I'm going to give it positive. So it means E net is going to be E PS plus E RS, no, not EPS, but yeah, PR, which is negative 60,000 plus 22,222.22, and that's going to give me negative 37,777.78 newtons per coulomb. It's negative, so it's going to be downward. Okay, and now question 8, the last question. We have 3 resistors that are connected to a battery with an unknown EMF and an unknown internal resistance, small r, as shown in the diagram below. Ignore resistance and the connecting wires. So we are ignoring the resistance of the connecting wires. And then the first question, in the definition of the EMF of a battery given below, A and B represents missing words or phrases. So the EMF of the battery is the maximum supplied by a battery per passing through it. So write down A and B in your answer book. So our A, we know the definition of EMF is the maximum energy supplied per coulomb charge, coulomb charge passing through it. Okay, and then question 8.2, with switch S closed, the voltmeter reads 2.63 volts. So now we are closing switch S, and then the reading is 2.63 there on the voltmeter. Calculate the equivalent resistance of the circuit. So the equivalent resistance is the total resistance of the circuit. So since we have a parallel and with this branch it further becomes a series. We have 1 over R effective equals to 1 over the 7 ohm plus 1 over the 4. Okay, I'm not supposed to put the ohm there. 1 over the 4 plus 3. So this is the same as 1 over 7 plus 1 over 7, and that's 2 over 7. But now because we are looking for R effective, remember it becomes the reciprocal, that is 7 over 2, and that's 3.5 ohms. So that would be R effective is 3.5 ohms. Then switch S is now open. So now they open switch S and the voltmeter reads 2.8. So now they want us to calculate the internal resistance of the battery. So when they open switch S, it means they eliminate that 7 ohm resistor, because there won't be current flow there since the switch is opened. And it would mean that we are now only using just the short circuit with 4 ohm and 3 ohm resistors in series. They want us to find internal resistance of the battery. Internal resistance and EMF were both unknown, but one thing that we should know about EMF and small r is that they always remain constant when switch closes or opens. They will be the same because the resistance, the internal resistance, is due to the nature of the battery, then the EMF is due to the internal resistance. So they remain constant. They don't change, meaning now I'm going to use, because it's 8 marks, I'm going to opt in for a simultaneous equation. So because I lack space, I'm gonna squeeze in everything there. So I'm going to first say, for the first equation, it's when the switch was closed. So when the switch was closed, we have EMF equals to I R plus small r. We didn't have EMF, but when the switch S was closed, what was the current? We need to find that, okay? Because we need to find I. Because we have, when switch S is closed, we have the reading on the voltmeter, we have R effective. So it means current would be equals to V over R, which is 2,63 over 3.5, and that gives me 2,63 over 3.5. That gives me 0.75 ohm. And then it means I'm going to plug that in my EMF equation. 0.75 R effective, big R effective is 3.5 plus small r. And then I'm going to say, for the second case, it's when switch was opened. Switch was opened. I still have EMF is I big R plus small r. My I is V over R. The V reading when the switch was opened is 2.8, and R, the total resistance is gonna change because now we're only working with the 3 ohm and the 4 ohm, so we just add them, then it's 7. So it's 2.8 plus 7, divided by 7, and 2.8 divided by 7, that gives me 0.4 amperes. I need to come back here and fix that. That is not ohms, sorry guys, that is amperes. So now I have the two. It means I'm going to substitute the I, 0.4, big R is 7 plus small r. Then now, because we have two unknowns that are common in both the equations, EMF and that, I'm going to equate the EMF. So I'm going to say 0.75 3.5 plus small r equals to 0.4, 7 plus small r. And if I multiply those together, I now have 0.75 times 0.35. That gives me that's 0.75 times 3.5. That gives me 2.63 plus 0.75 r equals to 0.73 0.4 times 7. 0.4 times 7, it gives me 2.8 plus 0.4 r. So I'm just going to move the numbers to the one side. So 0.75 r minus 0.4 r equals to 2.8 minus 2.63. So 0.75 minus 0.4, that gives me 0.35. 0.35 r equals to, and then 2.8 minus 2.63, that gives me 0.17. So r is 0.17 divided by 0.35, and r is 0.49 ohms. So that would be the value of small r. So they also wanted the EMF. So for EMF is I'm gonna use any of, I can use that or I can use that one. So I'm going to use the 0.4 because I found small r, so that's 7 plus 0.49. So 0.4, 7 plus 0.49, that gives me 2. Why is the EMF so small? 2.996 volts. So that would be 3 volts. That's the EMF. Then we have it. That's all. You'll see, guys, I'm not gonna do question 9 because it's not part of the June exam according to the scope. So yeah, this is all we had under this question paper. Most of you are writing tomorrow, so I hope this is going to help you. I hope you will gain some foundation, great foundation, to attack tomorrow's paper. Thank you so much, guys. Bye bye, and don't forget to subscribe.